Have you ever wondered how to teach computers how to solve problems for themselves? Maybe you've heard that Google has taught a computer how to play classic Atari games, given nothing more than the pixels on the screen during gameplay and the current value of the score. Or maybe you've heard of the Large Hadron Collider and the Higgs boson and wonder how physicists probe the fundamental properties of our universe. This summer, I've worked on using deep learning, the same algorithms used in Google's Atari playing computer, to classify collisions in particle colliders like the Large Hadron Collider, or LHC for short, where the Higgs boson was discovered in 2012. Even though I mainly work in Newland Science Hall at Notre Dame, the data I work with comes from all the way across the Atlantic. The LHC is located on the border of France and Switzerland. It is the largest machine in the world. To get a sense for just how large, that's an airport in the lower right-hand corner of the screen. There are multiple experiments at the LHC, but the one I work on data from, the Compact Muon Solenoid, or CMS for short, is located the furthest north. To produce the data I work with, two beams of protons are accelerated in opposite directions around the LHC. After accelerating for 20 minutes to a mere 3 meters per second slower than the speed of light, the beams are collided at the center of CMS, producing showers of particles that interact with the various parts of the detector. From CMS, I get a list of numbers describing how hard each object struck the detector and in what direction it was going at the time of impact. The problem is, even if a Higgs boson is produced in a proton-proton collision in CMS, it decays. And these decay products, which look nothing like the Higgs boson, are what's actually registered in the detector. So instead of seeing a Higgs boson, I see jets of quarks, electrons, photons, and not a Higgs boson. So even though only certain collisions produce Higgs bosons, there are a lot of other less interesting collisions that produce very similar products to a collision that does have a Higgs in it. Though deep neural networks, and more broadly deep learning, have been successfully applied to projects ranging from Google's self-driving car to their Atari playing computer, their application of problems in physics has lagged behind their application in other fields. My goal is to help physicists apply these powerful computational tools to their search for the fundamental properties of our universe.